Cool. So yeah, thanks for all of you who have made it this far. I know we're nearing the end of the conference, so I'll try to keep this talk short and sweet. So, what problem are we interested in? So, as Ronit said, we're interested in robust learning. So we want to know, what things can we learn even in the presence of errors? We're actually going to allow the errors to be malicious. So just to make the model a bit more concrete, we're mainly going to be focused on robust mean estimation. So here we're given a data set of n points that are vectors in d-dimensional space. Most of them, 1 minus epsilon fraction, come from some distribution p star that we care about. But the remaining ones can be outliers. And we're going to make no assumptions about these outliers. So you could imagine that they're actually chosen by an adversary who has knowledge of our algorithm and is trying to make us do poorly. And our goal is to estimate the mean of the true distribution. We'll also, in some cases, be interested in just deterministic point sets as well. But for now, you can think of things as being drawn from a distribution. So these blue points might be the good data. An adversary is going to add in some outliers, and if we just naively took the mean, we might be very far off. And you could imagine that you could do something like detecting these outliers and removing them, and then hopefully getting a much better mean. But it turns out that this is a natural strategy, but things actually start to go quite wrong in high dimensions. So let me explain what goes wrong. To see what goes wrong, we can take maybe the simplest example you could imagine, just a d-dimensional Gaussian with independent noise in each coordinate. And what happens here? So basically the problem is that even for this Gaussian, almost all of the clean data is going to be very far away from the true mean. So this is just because of how L2 norms work. Each coordinate is going to have variation approximately 1, and there's d coordinates. So all of these points are going to, with high probability, be square root d distance from the mean. So an adversary could play points even that all have high probability, the same probability as all of the good points under the Gaussian, and nevertheless shift the empirical mean of the data by something that is growing as epsilon, the fraction of outliers, times the dimension square root of d. And this bound is in most settings of interest, this bound is basically not going to be meaningful. So you hope to do better. But the point is that if you want to do better, you're going to have to do something subtle. Because here, even if we somehow had an oracle that knew the true density of the clean data, if they just look at points one by one to decide whether to keep them or not, they're not going to be able to do well. So we're somehow going to need to look at population level correlations in order to do something good here. And perhaps as a result of this, it's actually only quite recently that there's been bounds that kind of get rid of these dimension factors. So if you don't care about efficient algorithms, actually there's been something known since the 70s called the Tukey median that does do well here, but it's known to be NP hard to compute, and other estimators that had been proposed had high error and high dimensions. And it was only in the last couple of years, actually, from the TCS community that concurrent work by Dike, Nicholas, Kamath, Kane, Lee, Moitra, and Stewart, and Lyra and Vimpala gave the first dimension-independent error bounds. And since then, there's actually been a pretty considerable body of work, and also over the last several years, work in other areas as well, that I'm not going to have time to go into this, but sort of our motivation is going to be to try to unify some of this work, at least at kind of a conceptual level. So we're going to be interested in, are there some sort of general and simple properties that are going to enable robust mean estimation? And the motivation here is that even though there's been a lot of work in this area, a lot of the algorithms have been quite complicated. I feel okay saying this because some of the algorithms are from us, and actually when I've described them to people have told me they have like no clue what's going on, and they told me I should come up with something simpler. So I think So this is actually what the goal of this talk is to come up with something simpler, and to make our lives easier, we're actually not going to care about computational efficiency for now. So we're just going to care about the information theoretic picture, and later I'll maybe return briefly to computation. And so what we're going to do is we're going to propose a property, actually a deterministic property that a data set can satisfy called resilience, which is going to enable robust mean estimation. So here's the property. So we're going to imagine we have a collection of points in d-dimensional space that we're going to think of as being the clean data. And we're going to say it's resilient intuitively if every large subset of it has approximately the same mean. So to make this formal, we need to add in some parameters. So we're going to say that a set is sigma epsilon resilient in some norm around a point mu if every large subset of the set, so every set of size at least 1 minus epsilon of the total points, satisfies this condition. And this condition is just saying that if I take the empirical average of the points, their distance from mu in the norm is at most sigma. So again, this is saying every large subset has a similar mean. You can think of it as sort of a notion of robustness, but we're interested in robustness to added outliers, and this is saying actually we're thinking instead of addition robustness, we're thinking of deletion robustness. So this is saying even if an adversary could delete some of the points, the mean would still be similar. And the sort of main result here is going to be that resilience is going to enable robust estimation in a fairly general sense. So if we say that we have 1 minus epsilon n good points, which is going to be a resilient set, and a set of epsilon n arbitrary outliers, and we observe the union of those sets, then the theorem is that as long as the good points are resilient around some point mu, we can actually recover mu with small error, even in the presence of these epsilon n outliers. And actually, it turns out that the algorithm for doing this is very simple. We just have to, well, it's an exponential time algorithm, so it's not fast, but it's simple to describe. We're just going to look at all of the sets of size 1 minus epsilon n. We're going to find one that's resilient, and once we find one that's resilient, we're just going to output the center of that set, and that's going to be guaranteed to be close to the true set. So why is this? It's actually a pretty simple pigeonhole argument. So if there's only one slide you get out of this talk, I want it to be this slide. So also feel free to ask any question. Well, you should always feel free to ask questions, but definitely ask questions on this slide. So the basic claim is that if I have two sets, and they're both resilient around points mu and mu prime, and they're both large, then their means have to be close. So why is this? Well, we have this our entire set S tilde, and we have S, which is some large subset of it, but S prime is also a large subset of it. So what are we going to do? We're going to look at the intersection, and we're going to look in particular at the empirical mean of the points in the intersection. So first of all, by pigeonhole, since these sets are both really large, they're almost all of the set. Their intersection is also almost all of the set. So their intersection is a large subset of both of them. So therefore, the center of S prime is close to the mean of the intersection by resilience of S prime. And similarly, the center of S is close by resilience of S. And so then it's just the triangle inequality. These two things are close. So are there any questions about this argument? OK, so this shows us that before we had the statistical problem of when can we it's like maybe not even clear what properties you would need to assume about your distribution to recover things. The nice thing is now we've sort of reduced the statistical problem to an algorithmic problem. So as long as we can establish resilience with high probability, now we just have to solve this algorithmic problem of finding a resilient set. And I should probably show you some cases where things actually are resilient. So the first situation is if a data set has bounded covariance, it turns out to be resilient with parameter that goes as square root of epsilon. And this is in the L2 norm in particular, although you can generalize this to other norms. And the proof is sort of just a few lines of algebra. So don't worry if this doesn't make sense, but just to go through it quickly, if I had an epsilon fraction of points that was much more than 1 over root epsilon from the mean, then that's going to necessarily make the variance much larger than 1. So we know that any epsilon fraction of points has to, on average, not be too far from the mean, and therefore deleting any epsilon fraction of points can't shift the mean by too much. It can only shift it by epsilon times 1 over root epsilon, which gives us this square root of epsilon. So this is why you're resilient. And so this implies in particular that if the clean data has bounded covariance, its mean can be estimated to area root epsilon, even in the presence of epsilon and outliers. And for now, I'm kind of glossing over finite sample bounds. So you can either think of this as if the empirical covariance of the data is bounded, or I've drawn enough samples from a distribution. And I'll briefly talk about finite sample bounds at the end, but only very briefly. So I also just want to stress again, this isn't necessarily an efficient algorithm. This is just an information theoretic result. And we can actually, we can sort of generalize this. So if instead of bounded covariance, we have bounded kth moments, then the mean can again be estimated, where now instead of epsilon to the 1/2, we have epsilon to the 1 minus 1 over k. And eventually if you had all of your moments, you're going to get something like epsilon with polylog factors at the end of the day. So this is the first set of results, which is applying resilience in the L2 norm. But the nice thing here is actually that we can handle any norm we want. And it turns out for some problems, some other norm is going to be more natural. So often in combinatorial settings, the L1 norm is more natural than the L2 norm. So one setting which is actually going to be covered in much more detail in a couple talks is this sort of learning from batches. So we observe samples from a distribution on just a discrete set with m elements. And the thing that's going to help us is the samples are going to come in R tuples, which are either all good or all outliers. So we want to somehow use the fact that we get these batches and we know that they're either all good or all outliers to do something. And so what we can show is that the distribution pi can be estimated in TV distance to an error that basically, other than this log factor, it goes as epsilon divided by the square root of r. So these batches are sort of helping us by allowing us to kind of cancel out error by this root r factor. Note that if we didn't get these batches, it would actually be impossible to get a TV distance better than epsilon, because the adversary can always kind of perturb the distribution by epsilon and TV distance by adding epsilon outliers. So this is showing that the batches help. Again, this is not efficient. It comes from resilience in the L1 norm, and Chow and Valiant in 2 talks are going to give an algorithm for actually doing this efficiently. So I'll let them talk about that. The final cool thing is that we can actually handle the case even when the majority of the data are outliers. So where the picture sort of looks like this, where S, the good set S is this like tiny fraction of the set, and almost all of the data is controlled by an adversary. It seems like you shouldn't be able to do very much here, but it actually turns out the same basic pigeonhole argument works with just a little bit more elaboration. So basically what we're going to do is we're going to cover S tilde by a bunch of sets that are all resilient. By pigeonhole, at least one of these sets is going to have large intersection with the true set. And so that set is going to have center close to mu, just like before, by the same argument. And so this actually allows us to learn in what's called the list decodable model introduced by Balkin, Blum, and Vimpala, where we're just going to output the center of all of these green sets, and we'll know that at least one of them is good. And one implication in particular that this gives you is robust learning of stochastic block models. So in general, you can think of this setting as getting at robust learning of mixtures, because you can think of one of the mixture components as the good data and the remaining as the outliers. So here the model is that we have an alpha fraction of good points. We have a 1 minus alpha fraction of bad points. So this is a graph, right? So these blue and red things are the vertices. Among the good vertices, we have dense connections between good vertices that are random with average degree A. We have sparse connections between the good and bad vertices, again random with average degree B. But then the bad vertices get to choose adversarially how they want to be connected. And the question is, when can we recover this good set as a function of its size alpha and these degrees a and b? And using resilience in a sort of truncated version of the L1 norm, we can show that the set of good vertices can be approximately recovered whenever this criterion holds. So this is basically, a minus b. This is the difference between the internal and external degree of the good sets. So this is sort of saying, if this gap kind of normalized by the average degree is large compared to, 1 over alpha squared, which is the size of the set, then we're going to recover things. So this formula is kind of complicated. Don't worry about it too much. But the main cool thing for those of you who like to think about stochastic block models is that this actually turns out to match the Keston-Sigum threshold up to log factors, which is a sort of important threshold in the stochastic block model literature. And in particular for planted clique, which is maybe more familiar, it says that you can recover cliques of size square root of n log n, even if the connections outside of the clique are allowed to be arbitrary. So it's not the general. Well, so first of all, this isn't like an efficient result, so it doesn't like refute anything about planted clique. But also, things are not completely arbitrary. We're using the fact that the connections between the clique and the rest of the graph are all random. It's just that the connections outside could be arbitrary. And in other work, we actually have an information theoretic lower bound showing that you at least can't do better than root n. So this result is actually tight. So these are sort of the information theoretic results. As I promised, I'll briefly touch on algorithmic results. So you can sometimes turn these information theoretic results into algorithmic results. The basic obstacle is at least most of the algorithms that I know of right now that can do things efficiently rely on properties, basically rely on bounded covariance of the data. So we're not going to do anything magical that's better than that, but we're at least going to show that resilience is connected to this bounded covariance property. So we show that as long as the norm is strongly convex, a resilient set can be pruned, so you can sort of remove some number of points to make the remaining points have bounded covariance. And then separately, we show that as long as you can solve a certain approximation problem, then anytime you have bounded covariance, you're going to be able to efficiently recover the mean with this square root of epsilon error rate. So we're not going to be able to efficiently beat this root epsilon error with this algorithm, but you can at least get down to root epsilon. And the nice thing is both of these assumptions that we need are actually going to be true for LP norms. And it's possible to also make things happen in non-LP norms. So for other work that does that, there's work at Colt by Lee and by Du, Balakrishnan, and Singh that does this for a sort of sparsity-inducing norm that is not an LP norm. So other stuff in the paper, as I mentioned, we have sort of finite sample bounds where if a distribution is resilient, you can show that with high probability samples from it will also be resilient, and we have extensions from mean estimation to singular value decomposition. So just to summarize, we've presented this information theoretic criterion. In all of the settings that I know of, it seems to give tight bounds if you choose the norm correctly, and it's sort of nicely based on just a simple pigeonhole argument. It has this benefit where we've gone from this statistical problem to just having this algorithmic problem of finding resilient sets. And I think there's a lot of interesting directions to go in from here. So one question is sort of what's the right generalization of resilience to other problems such as regression? Can we come up with efficient algorithms under assumptions other than bounded covariance? And can we actually get matching lower bounds? Thanks.
Maybe this is what you mean by matching lower bounds, but is there, do you know any intractability for getting efficient algorithms?
That's a really good question. So I actually do not. I've thought about it because it does seem like, it's this interesting mixture of mostly statistical and a little bit of adversarial. So I don't know of anything, but I think that would be super interesting.
So maybe I missed it, but at some point you said that this
Yeah, so they.
Because it appears that the covariance-bound-based results should actually work even for the adversarial additive and deletive contamination, right?
Yeah, so basically, if you have a resilient set and like resilience is itself resilient, so if you have a resilient set and you delete some points, then it's still going to be resilient with sort of like slightly worse parameters. So this should also hold in the deletive model. The place where you run into trouble is in the case where you have a majority of outliers, because then it's actually like not super clear how you should define the deletion model.